Hi everyone, my name is Matthias and I'll be talking about tractable fragments of conjunctive queries with negation. So I'll start very briefly by recording the setting. It's the same as normal conjunctive query answering, but we also allow negation before atoms. We'll be interested in the associated decision problem. Given a query and a database, is there an answer for the query over this database here? Then what is the question we're following here? Well, we're interested in the combined complexity of this problem and in particular in tractable fragments of this problem. So why tractable fragments? Well, because of course this is a generalization of just plain CQ answering, which is already NP-hard, so this is also NP-hard. And importantly, the problem with negation is even NP-hard when we just consider alpha acyclic queries. So alpha acyclic queries are important because they are an important special case that is tractable for plain CQ answering. There are a lot of technical tools and developments on top of alpha acyclicity, like hypertree decompositions, that extend this tractability for plain CQ evaluation. So, and all of this no longer works in this setting. However, the story doesn't end here, and in fact, for a more restrictive type of acyclicity, called beta acyclicity, the problem is in fact known to be tractable. As common with these hypergraph acyclicity notions, there are a number of equivalent ways to define them, but we are interested particularly in this definition here. I'll be implicitly switching back and forth between the hypergraph of the query and the query depending on context. The hypergraph of the query is simply the same as in the normal conjunctive query case, so the negations play no role in the construction of the hypergraph. So now talking in the hypergraph world, I will use IV to be the set of incident edges of a vertex V. We can then define this notion of a nest point, which is as a vertex of the hypergraph where the set of incident edges is linearly orderable by subset inclusion. And then there's this very nice characterization of beta acyclicity, that hypergraph is beta cyclic if and only if the empty hypergraph can be reached by successive removal of nest points and empty edges from H. So you have an elimination ordering through nest points. So just a very quick example to make this clear. We have this very simple hypergraph, 2 edges and the 4 vertices A, B, C, D. If we look at vertex A to start, we see it has only one incident edge, of course, and is therefore trivially a nest point. On the other hand, if we look at C, both edges are incident, and of course these edges are incomparable by subset inclusion. So C is clearly not a nest point. But importantly, once we remove A, then C becomes a nest point. And so we see how this can be eliminated overall, and this hypergraph is beta acyclic. As we said, beta acyclicity is more restrictive than alpha acyclicity, actually significantly more restrictive. And so the natural question then is whether we can generalize beta acyclicity in such a way that we preserve the tractability of CQs with negation. And there have been essentially 2 approaches to generalizing beta acyclicity. First is beta hypertree width, where you just take the maximum hypertree width over all subhypergraphs. And the second one is point width, which is very new. And this is too complex, sadly, to recall here in full, but it has algorithmic applications. It induces tractable fragments for max CSP when given a decomposition, but finding a decomposition is unlikely to be tractable. However, to cut this short, neither is a satisfying answer to our question. They both aren't known to induce tractable fragments for CQs with negation, and it doesn't seem likely that they do. So nonetheless, the CQs with negation are an important problem, and we don't want to stop here or give up here. So what is done in the paper is therefore to generalize the idea of nest points to nest sets, as we call them. So we will use now IS, where S is now a set of vertices, right, not just a single vertex, to denote the set of all edges incident to any vertex in S. So alternatively, think of the union of the individual sets of incident edges. We again care about the linear orderability and the subset inclusion, but not directly on the set IS, but we have this intermediate set I star here, which as we see is simply IS, all the edges in IS, but we cut out the vertices of the nest set, or of the set S. And if this I star is linearly orderable by subset inclusion, then this is a nest set. So again, I think a quick example will clear this up. So we have this basic hypergraph here, and we want to find a nest set particularly with 2 elements. And if we consider now A and B, the set AB, and check whether this is a nest set. We see on the top here, set I star. You can easily construct it directly, right? You have A, B, C, D, you cut out AB, you're left with DC, which is the first set here, and the others are constructed the same way. But as we state here, this is not a nest set, as DC and ED are incomparable. On the other hand, if we look down here, on the bottom right, we have vertices C and F, and on the top, the I star is very easy. There is indeed a linear order over this I star set. However, note that it's important that we remove C and F here from the sets, because of course A, B, C, D and DCF are incomparable again. Again, we're interested in elimination orderings, but now of nest sets, not nest points. So this definition is just a technical way of saying delete nest sets successively until you reach the empty hypergraph. And we will call this a nested elimination ordering, or a NEO. And where this really becomes interesting is once we limit the size of the nest sets. So we call something a K-NEO if it's a NEO that consists only of K-element nest sets. And then we arrive naturally at the width notion, which we call nest set width, which is simply the minimal K such that there exists a K-NEO. So the smallest number where this size of nest set is enough to eliminate the hypergraph. So now we have this new notion, but this is not the goal, of course. So going back to our question before, we of course want to know if these NEOs actually have any algorithmic use for solving conjunctive queries with negation. And yeah, little surprise at this point in the talk, but yes, they do. They can be used to efficiently solve CQs with negation, and that's what we'll roughly discuss in the rest of this talk. We sadly don't have time to really get into the details of how this works, but I think the high-level idea here will make the basics of it clear enough. And so the basic idea is simply to eliminate sets of variables in the query according to the NEO. And this is similar in a way to how hypertree decompositions and similar techniques ultimately allow reduction to an alpha acyclic query, but it's slightly different in that nest sets will allow us to reduce to sort of locally beta acyclic cases. So we don't globally make the whole hypergraph beta acyclic, but step by step we make the relevant parts beta acyclic, as we will see on the next slide. To do this essentially for every nest set, there are 2 steps. First, we take this set IS and we extend every atom in IS to be incident to all variables in S. So we make it include all of them, or the whole nest set, instead of just parts. The second step, we eliminate the variables individually, like in the beta acyclic case. Well, it's similar to the beta acyclic case here. It's not exactly the same for some technical reasons, but the idea is the same. So if we look at this example query here with the nest set ABC, the query is drawn on the left side. We will only be looking at the hypergraph representations, so don't worry too much about the actual literals up top here. And on the right side, I've just drawn out the atoms or the edges that are actually incident to the nest set. So this is our set IS. So as said before, in the first step, we extend each of the atoms to contain A, B, and C. So each of the atoms should contain them now. On the right, we see the result of this extension on the hypergraph level, and on the actual query level, there are some details to deal with to do this, but at its core, the idea is simply to take the product with the domain. Importantly, this extension will always create this kind of nesting that we see on the right side. So this subhypergraph is always beta acyclic, and importantly, all of the vertices of the nest set become nest points, as you see here. And yeah, once all of them are nest points, essentially we can now eliminate each variable as in the acyclic. Because in the acyclic case, the algorithm eliminates nest points one by one. We can now do this on this subhypergraph for the variables in the nest set. And if we eliminate them, we arrive at this final hypergraph of this step. So we call this an S elimination, eliminating the set S. So what we can then obviously do is we just step by step through the whole nested elimination ordering, we eliminate all the variables from the hypergraph. We're left with a single tuple that has no variables, which is then trivial to solve. And by the equivalence, so this correctness statement, this solution will be a solution for the original conjunctive query with negation. So we of course need a neo to do this. We didn't have time to get into this here, but computing a neo is indeed tractable under bounded nested width. And so putting this all together, we get this main result here, that indeed bounded nested width induces new tractable fragments for this conjunctive query with negation problem. So to very quickly summarize, we introduced this new notion of nested width that generalizes better acyclicity to define new tractable fragments of the Boolean conjunctive query problem with negation. There's a lot more in the paper. We have also a tractability result for SAT, and even fixed parameter tractability actually, and there's some technical other results here. Well, there's a lot of future work to do, as all of this is rather new. A more efficient algorithm that works in practice would be nice, as the problem has applications in practice, of course. We would like to also study this for other problems. Sharp sort, for example, is also tractable under better acyclicity, also through nest point elimination, so there are very natural candidates to extend this here. And finally, the one relationship between nested width and other width notions that is left open in the paper is to point width, and that would be very nice to close the gap. Good, that's it for this talk. Thank you for your attention, and please, of course, feel free to contact me at any time if you have any questions.